Okay, this is section 1.2, functions given by tables. So our first major topic is functions given by tables. Now, there are certain situations where function values are given in a tabular form instead of given by a formula. My example here is that the population of a city may be given every few years, or the height of a child might be given on the child's birthday for the first few years of the child's life. So there's no function, you just kind of record data. So when you evaluate a function given by a table, you simply look at the value of the dependent variable that corresponds to the value of the independent variable, provided the value of the independent variable is also in the table. That's going to be the problem, is what happens if the value of the independent variable is actually not given in the table. If we had a formula, we could just plug the number into the formula. But with no formula, we have a problem. So some examples here. Our first one says, below is the table for a function f of x. We're going to evaluate the following: f of 1, f of 3, and f of 5. So here are my x values. Here are my f of x values. Notice the x values just go 1, 2, 3, 4, 5, 6, 7, 8, and the corresponding function values are given right there. Now sometimes instead of having like a horizontal rows like this, I might have a vertical table of values. The horizontal just takes up less space. That's the only reason I gave it horizontally. So for part A, f of 1. So here is x being 1. The corresponding functional value is 12. So f of 1 is 12. You can see this is a lot easier than doing some number crunching. It's just a matter of, can you see the table? So for part B, f of 3, okay, here's x is 3. The function value is 19. So f of 3 is 19. And for part C, f of 5, okay, here's 5 for x. There's its corresponding function value. So f of 5 is 26. Okay, so not too bad. Now sometimes we read the table backwards, which means I give you the functional value, you find the x value that goes with it. So it's kind of looking at the bottom row first. So for our second example, we're going to do something like that. Number 2, below the table for a function f of x, evaluate the following. If f of a is 21, what is a? And for part B, if f of a is 55, what is a? So again, it's the same table we had in example 1, I believe, yes. Okay, so for part A, f of a is 21. So we're looking for a function value of 21. There it is. And we look for the x value that corresponds to it. It's 4. So it's f of 4 that's 21. So our a is 4. For part B, f of a is 55. What is a? So we look for 55 in the f of x row, and there it is. So the x value that goes with it is 7. So our a is equal to 7. Again, it's not too bad if all the values that you need are actually given in the table. The real problem crops up is what happens if the value is not given in the table. Like for instance in this one, suppose I wanted to know what's f of 4.5 or what's f of 4.17. Those will be kind of nasty to do. So we want to look for a way to deal with that. So part 2, average rate of change. Okay, finding functional values for independent variables, for independent variable values not in the table. Like again, in the previous one, we were talking about f of 4.5 or f of 4.1. So we're going to figure out how to do it. So finding functional values for independent variable values not in the table. Occasionally we have to find functional value for the value of an independent variable that is not in the table. Depending on where the value of the independent variable is located in relation to the other values of the independent variables, it can be very easy or it can be rather complicated. We're going to take care of the easy case first. Like in the previous one, we were counting 1, 2, 3, 4, 5. So f of 4.5, you're halfway between 4 and 5. It seems reasonable to take a y value halfway between the two given y values. So if you're given a value of an independent variable that is exactly halfway between two given values, so again, exactly halfway between two given values, we take the average of the corresponding functional values in the table to obtain the value of the missing functional value. So we're going to illustrate how to do that with some examples. Remember, to find an average of something, just like for the average of two numbers, you add the two numbers and divide by 2. If you're looking for the average of 3 numbers, you add the 3 numbers and divide by 3. So that's the idea here. Some examples. Okay, again, I've got a table for f of x. I want to evaluate f of 2, f of 3, and f of 7. Notice my x's are just even numbers, 0, 2, 4, 6, 8, 10, 12, 14, and so on. And here are my function values. Again, we have no formula. And when I was making up this example, I did not have a formula either. I just made up some numbers. So the first part A, f of 2. Okay, notice x being 2 is in the table. So f of 2 is going to be 12, okay, just like the previous examples we did. For part B, f of 3, notice 3 is not in the table. But 3 is halfway between 2 and 4. So it's exactly halfway between two independent values given. So I want to take the average of these two values. That is the most reasonable guess, because again, that's what we're doing. We're guessing what the functional value would be. So to find f of 3, we compute the value that is halfway between f of 2 and f of 4. This is called the average value. Remember, to find an average for two numbers, you add them up and divide by 2. So f of 3 is going to be f of 2 plus f of 4 over 2. Add the two numbers, divide by 2. Again, 3 is halfway between 2 and 4, so I want to figure out what's halfway between these two values. So f of 2 is 12 and f of 4 is 22. So I have 12 plus 22 over 2. What is this? 34 over 2, which is 17. So f of 3 is 17. So again, this is called finding the average value. It depends upon the independent variable value being halfway between two values that are already there. Part C is f of 7. Okay, x equals 7 again is not in the table. There were only even numbers for the x's, but 7 is halfway between 6 and 8. So I'm going to take the average value of f of 6 and f of 8. So f of 7 will be f of 6 plus f of 8 all over 2. F of 6 is 18, f of 8 is 10. So 18 plus 10 over 2. We get 28 over 2, which is 14. So f of 7 is equal to 14. So this works nicely if our independent variable value is halfway between two given ones. Example 2 says the table below gives the height in inches of a fast-growing genetically engineered plant T days after it was planted. So I got values of T of 0, 4, 8, 12, 16, and there are my heights in inches. Notice these increase by 4 every time. I want to answer the following. In part A, what was the height of the plant when it was planted? Part B, give the functional notation of the plant 10 months after it was planted. And part C, find the height of the plant 10 months after it was planted. Notice B and C are related. Our solutions. Okay, for part A, the height when it was planted corresponds to T being 0. Because remember, T is how many months after you planted it. So if you just first planted it, T is 0. So for part A, when T is 0, the height is 8. So the plant was 8 inches high when you planted it. For part B, it says, give the functional notation of the plant 10 months after it was planted. So height 10 months after it was being planted is h of 10. I'm using h for height. And now I got to figure out for part C, the height of the plant 10 months after it's planted. That means I want h of 10. Okay, now 10 is halfway between 8 and 12, right? 8 plus 2 is 20, 20 divided by 2 is 10. So I am halfway between. So I need to find the average value of 19 and 31. So h of 10 is going to be h of 8 plus h of 12 over 2. So 19 plus 31 all over 2. See, 19 plus 31, I get 50 over 2, 25 inches. So the plant was 25 inches tall 10 months after it was planted. Oops, sorry about that. B, average rates of change. Let f be a function. The average rate of change of f of x between x equal a and x equal b is given by f of b minus f of a all over b minus a. It's kind of like where you were, or where you ended up with, minus where you were divided by how long it took you to get there. Okay, it's f of b minus f of a all over b minus a. That's the average rate of change of f of x between x equal a and x equal b. The physical interpretation of the average rate of change depends on what the function represents. So I'm going to give you a few examples, because sometimes you're going to be asked to interpret what does the average rate of change mean. So the meaning of the function, what is the function trying to tell you? Like, is it giving you height, giving you weight, something like that? And the meaning of the average rate of change. First one, if the function gives you your position at time t, the rate of change is the speed. In fact, you'll sometimes hear the phrase, you were traveling at a rate of instead of a speed of. So the classic example is rate of change is speed. Second one, if the function means the yearly value of an item, the meaning of the average rate of change is the yearly increase or decrease in value. It's like it's going up $15 per year, or it's decreasing $12 per year. A third one that I have is yearly population. So if the function gives you population, then the rate of change is giving you the yearly increase or decreasing population. Like the city is increasing its population at a rate of 10,000 citizens per year. Now it is just a nice little functional evaluation. This is the formula you use if you have a formula for the function, or if you have the function given to you in tables. Let's try some examples. Number one says let f of x equals 2x squared minus 5x plus 11. So I have a formula. I want to find the average rate of change of f between x equal 2 and x equal 5. Simplify your answer. Do not use mixed numbers or decimals in your answer. So our solution. I'm going to try this without a calculator. Okay, the average rate of change is going to be f of 5 minus f of 2 all over 5 minus 2. Okay, 5 minus 2 I can do is 3. Okay, f of 5, you're going to plug in 5 for the x, and for f of 2, you're going to plug in the 2 for the x. So I did my 5 minus 2 right there. Okay, this first set of parentheses, that's f of 5. 2 times 5 squared minus 5 times 5 plus 11. And this second set of parentheses, that's f of 2. I forgot to close my parentheses there, didn't I? So it's going to be 2 times 2 squared minus 5 times 2 plus 11. So we start doing some number crunching here. So the 3 stays the same. I'm going to have 2 times 25 minus 25 plus 11 minus 2 times 4 minus 10 plus 11. Now I have my closing parentheses back. Okay, this is going to be 50 minus 25 plus 11 minus 8 minus 10 plus 11. Still all over 3. Please don't lose your denominator. Okay, the minus 14 is negative 25 plus 11, just like the 1 is negative 10 plus 11. So I'm going to have, looks like 36 minus 9 all over 3. 36 minus 9, I get 27 over 3, which crunches out to be 9. Again, if you wanted to give this to the calculator, that's fine. So the average rate of change during that interval from x equal 2 to x equal 5 is 9. So a lot of messy number crunching. Be very careful with your number crunching. It's a shame to know what to do with a problem and then lose it on basic arithmetic. Number 2, the value V of a car t years after purchase is given in this table. So I've got t going from 0 out to 7 years. And here are my values. Okay, notice the car is losing value over time. Question A, find the average rate of change of the car during the first 5 years of ownership. And in part B, interpret the results of part A. In other words, what does it mean? Now please, when you're trying to tell me what something means, don't get carried away with it. Try to keep a nice, simple, declarative sentence. So our solutions. Okay, for part A, the average rate of change of the car during the first 5 years of ownership. So I want V of 5 minus V of 0 over 5 minus 0. Okay, 5 minus 0 is 5. Okay, V of 5, according to the table, is 17,200. V of 0 is 32,000. So that's 17,200 minus 32,000 all over 5. Then we do our 17,200 minus 32,000. We get negative 14,800 over 5. And then negative 14,800 divided by 5, we get negative $2,960. Remember, these are dollars. It's the value of the car. So there's your average rate of change during the first 5 years of ownership. Negative $2,960. Now, the interpretation of what this. Okay, this says that the car, because it's negative, the car is losing $2,960 in value each year for the first 5 years. If it were positive, it'd be increasing in value for the first 5 years. So this means that the car lost an average of $2,960 per year during the first 5 years of ownership. That's what part A means. Okay, using the average rate of change. Now that we've computed it, and part B of that last question was also kind of one use of it. What does it mean? Okay, we use the average rate of change in order to find a functional value when the value of the independent variable is not exactly halfway between two values of the independent that do appear in the table. So we're going to outline how you do this. This is basically interpolation. Whenever you're trying to find a functional value that is between two values that are in the table, you're doing interpolation. If you're trying to find a value that goes either above or below the table, you're doing extrapolation. So this is interpolation. So the method for filling gaps in a table when the value of the independent variable is not halfway between two table values. Remember, when it's halfway between, you just do the average value. So step 1, calculate the average rate of change between the smallest two values that contain the value of the independent variable in question. Okay? So it's like if the x's go 1, 2, 3, 4, 5, and you're looking for 4.1, you would find the average rate of change between 4 and 5. So this could be kind of messy. Step 2, calculate the number of values between the value of the independent variable in question and the smaller value used in step 1. This is done by doing value of independent variable in question minus smaller value from step 1. Again, like if I went 1, 2, 3, 4, 5, and I had 4.1, you're going to be looking at 4.1 minus 4, so it's 0.1. Step 3, multiply the value from step 1 by the value from step 2. Kind of tells you the incremental change you need. How much further up do you need to go? And step 4, add the result of step 3 to the smaller dependent variable value used in step 1. This will become a little bit clearer when we do some examples. Right now it's kind of vague. So I've got a couple of examples to illustrate how this works. But again, what we're doing here is interpolation. That's really what we're doing. And remember, this is all because the function is given to you in a table rather than in a formula, and you have an independent variable value that's not halfway between two given values. So we're going to illustrate the method with some examples. some examples. Number 1, the table below defines the function f. Use it to find the following values, f of 3 and f of 7. So my x's go 0, 4, 8, 12, 16, 20. I'm adding 4 every time. And here are my function values, 7, 12, 18, 11, 3, 12. Okay, so we're going to go through this according to what the steps say. So our solutions. Part A. Step 1. The value is x equal 3, which of course is not in the table, and it's not halfway between 0 and 4. But x equal 3 is first between 0 and 4. So we compute the average rate of change between x equals 0 and x equals 4. Okay, so this is step 1. We're going to find the average rate of change from 0 to 4. So it's going to be f of 4 minus f of 0 over 4 minus 0. Remember, that's your formula for average rate of change. F of b minus f of a over b minus a. Okay, the b minus a, that's 4. Okay, f of 4 is 12, f of 0 is 7. So I've got 12 minus 7 over 4. And that works out to be 1.25. Okay? I clearly took out a calculator. So that completes step 1. Okay, step 2, I want to figure out how much further past 0 do I need to go to get to 3. So step 2, the number of values between x equals 3 and, that should be x equals 3 and x equals 0. Okay, that one should be a 0 because that's the one I used, is 3 minus 0, which is 3. So change that 3 to a 0. In fact, let me go ahead and do it now. If it'll let me fix it. Okay, I want to make that one a 0. Okay. So let's get back to what we were doing. Okay. So the functional value that's given to me minus the lower x value. So I got 3. That completes step 2. Step 3, value from step 1 times value from step 2. Okay? Value from step 1 times value from step 2. So I'm looking at 1.25 times 3, I get 3.75. Okay, 3.75. Then step 4, I'm going to add this result to the lower functional value. So it's like I need to come up that much to find f of 3. So step 4, add the result of step 3 to f of 0. So 7 plus 3.75, I get 10.75. That's f of 3. So f of 3 is 10.75. Part B, we're doing f of 7. Okay, for step 1, notice 7 is first between 4 and 8. So I'm going to find the average rate of change between x equals 4 and x equals 8. So I'm looking at f of 8 minus f of 4 over 8 minus 4. Okay, 8 minus 4 is 4. So I'm going to have 18 minus 12 in the numerator. 18 minus 12 is 6. 6 over 4, I get 1.5. So there's step 1. Okay, step 2, the number of values between x equals 7 and x equals 4. Remember, 7 is the value in question, 4 is the lower value. But there I just used. So it's 7 minus 4, which is 3. Now remember, for step 3, I'm going to take this value times the value I got from step 1. Which, remember, from step 1 I got 1.5. So step 3, value from step 1 times value from step 2. So 1.5 times 3, I get 4.5. We now take this value and add it to f of 4. So step 4, add the result of step 3 to f of 4. So I have 4.5. So I'm looking at 12 plus 4.5. So I get 16.5. So f of 7 is 16.5. Now, kind of as a check, the value you get here should be somewhere between these two values. If you got like 27.3, you know something went wrong. Like, even though I don't have it as a problem, if I were looking for f of 9 should be something between 18 and 11. Otherwise, I've made a mistake. because the x value I have is between those two. The y value I find, or the functional value I find, should be between those two. So you have kind of a little check that lets you know your answer is clearly wrong, which is kind of nice. Example 2. The population of Wassenich for the last 5 census is given in the table below. Based on the table, estimate the population of Wassenich in the year 2017. Round your final answer to the nearest whole number, because fractional people don't make sense. So here are my years: 1970, 1980, 1990, 2000, 2010. Notice 2017 is beyond where the table goes. So in this one, we're actually doing an extrapolation. So our solution. So step 1, notice that 2017 is not between 2 years in the table. It's actually beyond that. Now, if we were looking at 1960, we'd do something similar. We'll use the average rate of change for the last 2 years in the table. If we were doing 1960, for instance, or we would use these two values. So we're going to use these two values for going to the right. We would use these two values for going to the left. So we're going to find the average rate of change between the years 2000 and 2010. So we're looking at 9,860 minus 8,105, right? Over 2010 minus 2,000. Okay, my denominator is 10. So I got 1755 divided by 10, which is 175.5. Okay, whenever we're supposed to round something, you save your rounding until the very end, even though it's not going to be impossible to round at this stage. But I'm going to save my rounding to the very end in case I have to add some other decimals to it. So the result of step 1 is 175.5. So again, if you're going beyond the table in either direction, use the average rate of change for the last two values in the table. Either the last two on the right if you're going beyond to the right, or the last two on the left if you're going beyond to the left. Okay, then our step 2, the number of years between 2017 and 2010. It's 7, right? 2017 minus 2010. Okay, now we're at that multiply stage. Remember, multiply that result by that result. So step 3, value from step 1 times value from step 2. So 175.5 times 7, you get 1,228.5. Now again, even if we're going to the left side, it would still be the same. Everything would still be the same. Step 4, add the value from step 3 to the last population of the table. Then round to the nearest whole number. Now if we were going in this direction, we would, instead of adding it to the last value, we would subtract it from the last value. So I'm looking at, what, 9,860 plus what I get before, 1228.5. So 1228.5 plus 9,860, I get 11,088.5. Now you will round to the nearest whole number. So the nearest whole number of the population in the year 2017 is going to be 11,089 people in the good town of Wassenich. Okay, now we're going to be looking at trends and limiting values. Trends are sometimes like, is it increasing, decreasing, is it just wandering around aimlessly, that type of stuff. Limiting values is kind of like, does it look like it never goes beyond a certain number? So trends. A trend in the data is something like, can the values of independent and dependent variable both increase or decrease at the same time, or does one go up while the other goes down? Or does it cycle through, like sometimes it's going up, then sometimes coming back down, kind of like a population of deer that goes up and goes down over time. An example of the former would be the demand of a product decreases as the price increases, or performance on a test increases as the amount of time preparing for the test increases. An example of this cycle thing would be the average temperature at noon over a period of a year. Like it's warmer at noon in the summer than it is in the winter. So it's like the temperature would be going up and down, up and down. Now sometimes there is no trend, okay? So it's like some sort of random haphazard thing. Limiting values. Definition. A limiting value is a value that is the maximum or minimum value that a function can assume. So it's somewhat theoretical. A limiting value can be theoretical, a matter of practicality, or a value determined by physical limitations or law. Now when we say law, we're talking about laws of physics or laws of chemistry, not the laws of man. So oftentimes for safety reasons, the law may set a maximum occupancy level for theaters, restaurants, or other public places. Like some of you may have actually been in places where they yank people out because it's too crowded. It's considered a fire hazard. For those of you that know your algebra, these limiting values are sometimes referred to as asymptotes. In nature, there is often a limit to the population of animals in a certain geographic region. This is usually called the carrying capacity of the land. If there's only so much food and so much space, the animals will start to die off if they get too crowded. For a free-falling body, there's a limit to how fast the body will fall. That is called the terminal velocity. On Earth, at sea level, terminal velocity is about 120 miles per hour. So it's like if you're free-falling, it's a basketball, an anvil, or whatever, about 120 miles per hour. That's about as fast as it's going to go. Air resistance is what keeps it from going any faster. For ecology, it's the amount of food available on the land. Some examples. Susie has been studying the population of bass and lake trout for several years. Letting t equal the number of years since 1990, and p of t equaling the population of bass and lake trout t years since 1990, she has recorded the following results. Notice she's been recording her results every 5 years. It went from 325 to 385, 396, 398, 400, 400. Here are questions. Question A. How many bass were in the lake when Susie began her study? Question B. Based on the table, describe in words how the population of bass has been changing over time. Part C. Use function notation for the population of bass in the year 1998. Question D. Estimate the population of bass in the year 1998. Round your final answer to the nearest whole number. Notice 1998 is not going to be in the table, is it? Part E. Explain how the physical problem would lead you to believe that there is a limiting value for the population of bass. F. Make a table showing the average rate of change of the population of the, that should say bass, not deer, of the population of the bass during each 5-year period. If necessary, round final answers to 2 places to the right of the decimal point. In Part G, from the table, what does the limiting value appear to be? Again, this value is called the carrying capacity of the environment. So we got a bunch of things to do. Now, oftentimes in WebAssign, the questions are like this. You have one nice, simple, innocent question or problem, and then he gives you like 50 million questions to answer about it. Okay. Part A is how many bass were in the lake when Susie began her study. So, going back to our table, 325. So our solution, when Susie began her study, that was t being 0, right? She began her study, so there were 325. Question B, based on the table, okay, again looking at the table, the population of bass seems to be increasing, but the rate of increase appears to be slowing down, and in fact appears to be stalling out at 400. So, based on the table, the population of bass has been steadily increasing. It increased more rapidly in the early years and started to level off after about 10 years, right? Because it didn't increase, like only got 2 more bass in the lake and then 2 more again, and now you've stalled out at 400. The value for t for 1998 is 1998 minus 1990, which is 8. So I'm looking for the value of 8 in the table. And of course it's not there. But it is between 5 and 10. Unfortunately, it is not exactly halfway between 5 and 10. So I have to figure out the average rate of change between t equal 5 and t equal 10. So the population of bass in 1998 is going to be p of 8. So remember, for part C, we're just supposed to use function notation. Now part D, the fun part, we're going to evaluate p of 8. So it's between 5 and 10. So we're going to look at the average rate of change. So it's going to be P of 10 minus P of 5 over 10 minus 5. Okay, 10 minus 5 is going to be 5. We're going back to our table. P of 10 is 396. P of 5 is 385. So I'm looking at 396 minus 385 in my numerator. And I get 2.2. Remember, that's the step 1. Okay, that's step 1 in doing this function evaluation. So we're going to get that P of 8 is going to be P of 5, because remember, the lower value, plus the 8 minus 5, right? How many steps you have to go, how many values you have to go from the lower value that you use to get your average rate of change to the value you're looking for, times the value that you got from step 1. So I got 385 plus 3 times 2.2. Okay, all this stuff is combining steps 1 through 4. Okay, remember, this part right here, finding the 2.2, that's step 1. The 8 minus 5, that's step 2. 3 times 2.2, so this part right here, that's your step 3. And then that's added to the lower functional value that you used in order to calculate the average rate of change. So you get 385 plus 6.6, 391.6. So to the nearest whole, let's see, we're leaving that to the nearest tenth, weren't we? What did it say? Let me go back. Oh, nearest whole number. So to the nearest whole number, there are about 392 bass in the lake in the year 1998. Remember, this is step 1. 8 minus 5 is step 2. 8 minus 5 times 2.2 is step 3. And then add that to the lower functional value that you use to calculate the average rate of change. Question E. From the physical problem, the reasons that I believe that there is a limiting value for the population of bass are: the lake is not limitless. Okay, it's like the lake is only so large. We don't know how large it is, but it's only so large, so there can only be so many fish in the lake, even if there were no water in the lake. There's only so much food available for the bass. Okay, so if they can't eat, they start to starve and die. Other animals in and around the lake prey on the bass. Okay? After all, remember, this is called lake trout. And maybe there are fishermen out there also taking some of the bass. The average rate of change for each time interval. Okay. From t equals 0 to t equals 5. Because you're looking at p of 5 minus p of 0 over p minus 5. Okay. I switched to f for a reason known only to me. So I'm looking at 385 minus 325 over 5. You get 12. Then from t equals 5 to t equals 10, we're going to have f of 10 minus f of 5 over 10 minus 5. But the denominator is always going to be 5. Remember, these were done in 5-year increments. So we'd have to go back to the table to see f of 10 minus f of 5. So 396 minus 385 over 5, you get 2.2. So notice, in the beginning, the first 5 years, you were growing at a rate of 12 bass per year. Now you're only growing at a rate of about 2.2 bass per year. Okay, from t equal 10 to t equal 15, f of 15 minus f of 10 over 15 minus 5. 398 minus 396 over 5, you get 0.4. So the rate of increase has slowed down even more. You're only growing at 4/10 of a bass per year. Then here are my other calculations, from 15 to 20 and then from 20 to 25. Notice for the last year that I can calculate, the population of bass is not growing. And for this, from 15 to 20, it's growing at the same rate as it was for the previous 5 years. So we appear to be reaching a limiting value because the rate of change over each type interval is getting smaller and smaller, or it's getting constant, or it becomes 0. Whenever that happens, that does mean that there's limiting value. If you can get the average rate of change to remain at 0, or very close to 0, then there is a limiting value. So here's my table. There's my time interval, and those are the calculations that I made. So here, these were the calculations. So 12, 2.2, 0.4, 0.4, 0. So the limiting value, even using this, that the rate of increase is slowing down, limiting value is 400. So from the table, it looks like limiting value is 400. Kind of like, again, looking at that and looking at the table, the lake can only support about 400 bass. Question number 2. The temperature T, that's capital T, of a cup of coffee in degree Fahrenheit, little t seconds after being poured is given in the table below. So my time increment is going in increments of 10 seconds. And it starts off with a temperature of 100 degrees and goes down to a temperature of 76. My questions. What was the initial temperature of the cup of coffee? Describe in words what is happening, that should say, to the temperature of the cup of coffee over time. Use function notation to give the temperature of the cup of coffee 15 seconds after it's been poured. Estimate the temperature of the cup of coffee 15 seconds. And of course 15 is not in the table, but notice how nice. It is halfway between those two. Does there appear to be a limiting value for the temperature of the cup of coffee? Explain your answer. If you think there's a limiting value, what do you think it is? So notice there are 3 questions in that one. F, make a table showing the average rate of capital T of little t in each of the time intervals. If necessary, round your final answer to 2 places to the right of the decimal point. In question G, what does the value from part F in the time interval from t equals 0 to t equals 10 mean? Notice the time interval from t equals 0 to t equals 10 is the first one. So we're going to figure out what does that mean. Okay, before I flip over to the next slide, we can actually answer the first question. What was the initial temperature of the cup of coffee? Remember, that's when t equals 0. So the initial temperature was 100 degrees. So when the cup of coffee first came out and was set down on the table, it had a temperature of 100 degrees. Question B. We're supposed to describe in words what is happening to the temperature of the cup of coffee over time. It's decreasing. Okay, notice over time it's decreasing. Here it decreased by 10 degrees, then it decreased only by 6, but notice the rate of decrease is slowing down. So it appears to be leveling off to a temperature of around 76, maybe even 75 degrees. So what is happening to the temperature of the cup of coffee? It's decreasing, but at a slower rate over time. It's not like it does its fastest cooling as soon as you pour it. Then question C. Use function notation to give the temperature of the cup of coffee 15 seconds after it's been poured. That's going to be T of 15, capital T of 15. And then we're supposed to find T of 15, right? We're supposed to estimate this. So if we're going to find capital T of 15. Okay, now, little t equals 15 is halfway between 2 given time values. So we use the value halfway in the time interval from t equal 10 to t equal 20. So we're looking at the average value from t equal 10 to t equal 20. So it's going to be t of 20, that should say, okay, plus t of 10, all over 2. So I'm looking at 84 plus 90 over 2. Again, I got these values by going back to the table. Right, t of 20, t of 10. So to get the average value, add them up, divide by 2. So 84 plus 90 over 2, 87 degrees. So this one wasn't quite as nasty as the other. Again, when you're doing the problems in WebAssign, you may get ones that are really simple like this. You know, you're halfway between 2 given values. You just use the average value, or you might have to use the average rate of change. Okay, there does appear to be a limiting value for t. And again, when we looked at it, it appeared to be around 76 degrees, maybe even 75 degrees. So it appears to be maybe around 75 degrees. Now, why is that possible? The reason there's a limiting value is that the cup of coffee cannot get any colder than the temperature of the room. Okay, so it's kind of like the temperature of the surroundings. That's actually called the ambient temperature. And question F is to find a table for rate of change of t of t. Okay, so we're going to do the calculations for each of the time intervals from t equals 0 to t equals 10. T of 10 minus t of 0 over 10 minus 10. Remember, the denominator is always going to be 10 because we did it in 10 second increments. So I got 90 degrees minus 100 degrees over 10, negative 1 degree. It's negative because remember, it is cooling down. So from t equal 10 to t equal 20, 20 to 30. So here's my 10 to 20. Here's my 20 to 30. So it's negative 0.6 degrees, negative 0.4 degrees. So notice it's cooling down at a slower rate, but it is still cooling down. So T of 20 minus T of 10 over 20 minus 10, T of 30 minus T of 20 over 30 minus 10, and then, because I went all the way up to 60 seconds, so my next slide I'm going to have two more time increments. I'm going to go from what? T equal 30 to T equal 40, and then T equal 40 to T equal 50. So T of 40 minus T of 30 over 40 minus 30, T of 50 minus T of 40 over 50 minus 40. So negative 0.2 degrees, negative 0.1 degrees. See, again, they're getting smaller, but they're still all negative because remember, the cup of coffee is cooling down. And then I got one more to go, right, from T equals 50 to T equals 60. So T of 60 minus T of 50 over 60 minus 50. So it's also negative 0.1 here. Remember, the previous one here was also negative 0.1. So it appears to be the same. So they're all fairly close. Even though they're negative, these average rates of change are getting close to zero. So that does lead us to believe that there really is a limiting value. If your average rates of change start to get close to zero or work out to be exactly zero, that's your clue that you do have a limiting value. So when I make the table here, so remember, to get each of these calculations, like, T of 10 minus T of 0 over 10 minus 0, T of 20 minus T of 10 over 20 minus 10, T of 30 minus T of 20 over 30 minus 20, T of 40 minus T of 30 over 40 minus 30, and so on like that. And then part G was to figure out what does the value from part F for T equals 0 to T equals 10 mean. So we're wanting to know, what does this negative 1 degree mean? Okay, that's the final question of this example, is what does that negative 1 degree mean? So the value of negative 1 degree between T equals 0 and T equals 10 means that the temperature of the cup of coffee is decreasing at a rate of 1 degree per second for the first 10 seconds. Remember, the time was measured in seconds. If these were minutes, it would be decreasing at a rate of 1 degree per minute. So notice it's cooling down fairly fast. End of section 1.2.